8.5 years ago, I unboxed a petabyte of storage. It weighed over 150 pounds, required multiple servers, and used an ungodly amount of power. Theo Joe asked me, why not simply use one petabyte drive? We're not quite there, but we're getting very close. Each of the Kioxia LC9 SSDs in my hand holds 245 terabytes of data. That means with just 4 drives, I can hold nearly a petabyte of storage in the palm of my hand. That's thanks to the chonky thick NAND packages that it uses that each contain a whopping 32 stacked dies, all wired together with gold. And behind me is the Kioxia fab that made them, alongside the cutting-edge NAND flash that you might find in your other favorite electronics, mobile devices, and memory cards. It is one of the most advanced manufacturing facilities on Earth, and Kioxia was kind enough to sponsor this video and give us unprecedented access to their facility, from the very top to the very bottom. Ready. Let's just see if Kioxia is ready. Maybe I'm not ready. We're going to be taking you step by step through Kioxia's sprawling Yokkaichi plant that spans 7 fabs, over 694,000 square meters, and even has its own tennis court. All so we can turn this into this. Every semiconductor's story begins with purified silicon. It gets melted in a vat into which a single seed crystal is inserted. The vat gets turned while the seed crystal is pulled out, creating an enormous monocrystal. Now, the full-sized one would be too large and too cumbersome for me to carry, but I've actually got the top of one where you can see how a teardrop shape is formed as it is pulled out of the molten vat until it gets wide enough to grind down into the 300mm diameter wafers that are used to make semiconductor devices. In the fab behind me are thousands upon thousands of these wafers ripping around on automated tracks in carrier pods called FOUPs. Over the course of several months, each wafer will travel many kilometers, often over skyways between completely separate buildings, and will go through thousands of manufacturing steps before becoming a finished chip. These fabs take years to build, cost billions of dollars, and contain some of the world's most closely guarded secrets. The basics of semiconductor manufacturing are well known. Branch Education has an outstanding video on the subject. We'll have that linked down below. But what I want to focus on today are some of the specifics that make this fab especially tuned for crafting high-density storage chips. Welcome to Y7. It's one of the cleanest places on the planet, with so little airborne contamination that it would be about like having a single bee in a giant baseball stadium. This is incredibly important because just one single particle of foreign matter can spoil months of costly work. To create their cutting-edge BiCS Flash Generation 8 memory cells, Kioxia uses a process called Plasma-Enhanced Chemical Vapor Deposition, or PECVD. This allows them to turn chemical vapors in the vacuum chamber behind me into the 218 intricate storage layers that give these chips their incredible data density. Plasma CVD operates at lower temperatures compared to conventional chemical vapor deposition, allowing its use on substrates that can't withstand higher temperatures. You probably noticed that this isn't the only machine here. For mass production, semiconductor fabs contain hundreds of machines, many performing the same functions, and they pack them in tight. That makes sense, because clean rooms are extremely expensive to both build and operate. So the less you have to build, the more you save. So how do they pack things so tight? To find out, we'll be going somewhere I've never been before. Below the fab. We're in the belly of the beast now. You know what they say, behind every great fab clean room is an almost as clean sub-fab that contains the ancillary equipment that supports the manufacturing equipment above, including power, chemical supply lines, and in this case, a dry pump that creates the vacuum needed for our plasma CEVD machine that is right above us. But what about sub sub-fab. To optimize the layout of their fab, Kioxia is using an unusual second sub-fab, which helps them avoid spreading their ancillary equipment out so much, which improves equipment density and helps them avoid long, circuitous runs that can make maintenance more challenging. In this case, we're looking at gas neutralizing equipment, which treats the toxic gas that's exhausted from the CEVD equipment that is above us before it gets vented. Since we're down here, clean room airflow goes top to bottom. So fresh air comes in way up above where our plasma CVD machine was, then down through the fab, the sub-fab, and then ultimately gets drawn up down the sides of our sub-sub-fab before being sent back up to be filtered and reused. Coming back up to the main fab floor, we've got another really special treat for you guys. See, in traditional NAND flash, your CMOS logic layers would be manufactured on the same wafer below the flash memory cell layers. That sounds pretty good to me. Approved. But there's a small problem. The best conditions for manufacturing high-performance CMOS circuitry and high-density NAND are quite different. Kioxia's solution? What about second wafer? That's right. They produce the CMOS on an entirely separate silicon wafer and then literally sandwich them together with a nice smear of copper that bonds the two layers together. It's called CBA, or CMOS directly bonded to array. And thanks to some very complex and precise engineering, Kioxia is able to create a low resistance, high reliability bond, providing increased data density and performance. But wait, with two wafers, won't it be twice as thick? Yeah, it will. In fact, you can see it, and it's even noticeable just picking them up with my hands. How's that gonna help with storage density? Don't worry, they thought of that. Once the two are joined together, they quite literally grind off the excess silicon on the top of the sandwich, right down to the flash cells, and then the processing continues. Like, what? Surely this has gotta go wrong sometimes, right? Well, yeah. Let's visit the factory NARC, the scanning electron microscope, and talk about AI. I'm not talking no content slop. It's actually super legit. I probably don't have to tell you guys that one of these wafers is worth a heck ton of money. So minimizing defects is the difference between huge profits and happy customers and rapid bankruptcy. That is where AI data analysis comes in. Kioxia is collecting data around the clock, about 35,000 data points per second. And analyzing all of that manually is impossible. So they've been using AI since well before the current trend to gain insights into how to improve their processes and maximize quality. Let's have a look at how this works. On this laptop are some example defects from the scanning electron microscope grouped up by AI according to their type. I'm gonna try and guess what caused them. Wormhole fragments.
Scrape.
Okay. Easter bunny tears.
Scrape.
Dodo dandruff.
Scrape.
Unfortunately, the real answers are very critical to Kioxia's operations, so they shall remain a mystery. You win this time, AI. This time. But next time, I'll challenge you to show me a seahorse emoji. Then we'll see. Anywho, by using this information about defects, Kioxia can simulate fixes in their fab's digital twin and then roll that into production to improve their product quality. Enough about the small stuff though. I think the most impressive aspect of this facility is how big it is. We're standing on one of the Y7 fab loading docks, where fab equipment can be lifted up to 7 stories on cranes for deployment inside. It's 3 million square feet, and that's not enough. They've already got plans to add even more capacity. Mind-blowing. Of course, when you're operating at this scale, you run into all kinds of challenges that most people don't even need to think about. Below me, for instance, is their on-site storage and management of gases and chemicals for semiconductor fabrication. It smells kind of like nail polish. And this is one of their on-site solar panel deployments that's part of Kioxia reaching their goals for green energy and sustainability. This one deployment has over 7,000 solar panels and can reach a peak power generation of over 2.5 megawatts. Another major environmental consideration for Kioxia is water. It's not the most intuitive thing in the world, but semiconductor manufacturing uses far more water than you'd think. And not just any water. In this glass is some of the purest water on the entire planet. It is so pure, in fact, that it is classified as a solvent, and in large enough quantities, it will actually extract minerals from my bloodstream. I asked Kioxia if I could drink some, and even though small quantities are unlikely to cause permanent damage, they forbade me. I was forbaded. So what do they use it for? Well, kind of everything, from cooling to wet etching to the many, many washing steps. If you need computer chips, you need ultra pure water, and you need ultra lots of it, which sadly means an ultra lot of waste. This is what it looks like after it's been used. The water behind me is full of acids, solvents, heavy metals, and all kinds of nasty things. But here's the thing, water's expensive, and also the environment is pretty cool. So Kioxia puts a lot of effort into water reclamation. This tank is actually part of their older water filtration system for their older fabs, but it's a little bit more visual, so we thought we'd take you through it. This first stage agitates a mixture of wastewater, biochemicals, and soil to facilitate easier filtration in the following stages. You know, they said I couldn't drink the ultra pure water, but they never said I can't drink this. No, I won't. The next stage is this gigantic mechanical skimmer vat that features a conical shape, allowing all of the sludge to easily make its way towards the bottom while taking off the purest water at the top. And it's amazing what a difference it makes. This is the before, which you just saw me scoop out. And this is the after, which we pull right out of the edge of this tank. Next, it goes through a second stage of mechanical filtration where it becomes so clean that fish can live in it. But don't take my word for it, take their word for it. This is the same water that is coming from that filtration station. And as you can see, there are koi living in it right now, sort of like water canaries living in a silicon coal mine. But as cool as the old water treatment system is, the reclamation rate is only around 80%, which is okay, but it's not nearly as good as the new system that came alongside the new fab. It's all enclosed, so we can't really show it to you, but it reclaims over 90% of all the water that's used that can be sent back into production for various purposes. Now, let's jump back inside. So now that it's out of the fab, our wafer is done and ready for human consumption, right? Well, not so much. See, using Kioxia's BixFlash Generation 8, this little square right here is up to 2 terabits of storage, which means that if we wanted to make an 8 terabyte package, like their latest dies, we would need 32 of these stacked on top of each other, which would get pretty thick pretty fast. That is where backside grinding comes in. We take this wafer and put a protective layer on top of it to keep all of our precious NAND flash safe. Then we put it in the machine behind me and grind away the back until it goes from being stiff like this to being middle-aged like me. In total, we go from about 0.8 millimeters down to anywhere from 30 to 40 micrometers, depending on the process. Much better for stacking. Stacked on what, you might ask? On the substrate, of course. On the bottom of this is what will ultimately be the BGA interface that will allow this NAND flash to be soldered to a phone or laptop or SSD. And then on the top is where we're gonna create stacks of these dies, up to 32. Oh my God, it's beautiful. Wow. Of course, before we can do that, we need to cut them up, and that's where die dicing comes in. The thinned wafer gets mounted to one of these frames, and then a diamond blade is used to cut out all the individual dies. Now let's talk about wiring them up. Every one of those stacks is connected using dozens of tiny golden wires, about a quarter of the thickness of a human hair. It's fed off of a spool like this into a tiny sewing needle-like capillary that touches every contact point. You barely make out what it's all connected to with the naked eye. So I won't try. Kioxia helpfully provided this microscope to give us a much better look. And you can see where every wire connects to the substrate. And then look at this, we turn it this way. Wow, we get a really good view of the stack. That's incredible. Incredibly fragile. How do we keep this safe? Inside this machine, trays get loaded with resin. It starts in a powdered form like this. Then our bonded dies go face down onto the resin, and the whole thing gets moved into these high temperature waffle irons. Then after a short cooling cycle, our now resin-protected die stacks are shoved out the front of the machine. In a mass production environment, these would move to the next stage in an automated fashion, but this is a small-scale prototyping lab, so our trays of very expensive bookmarks comes out of the machine, onto the cart, and then off to our next step. Behind me is a shaker tray that's full of these tiny little solder balls. This vacuum head comes over it, sucks up solder balls, and then carries them back to the backside of our substrate, precisely placing them on what will be the contact points where our NAND flash will be soldered to a board. The solder balls get melted in the oven behind me, then our trays get cleaned and dried. Laser engraving. Every one of these packages gets etched with the batch number, except, oh, one of them is actually missing its markings. That's because at some point, that package was tested and found to be defective. Whether it's one of the dies, one of the stacks, or one of the wire bonds, we don't know, but it's no bueno, so it doesn't get a name. These machines are wild. They can do a whole one of those trays in 60 seconds. Now it's party time. This machine slices, she dices, she cleans with ultra pure water, and even takes the dice packages and arranges them nicely on a tray, pretty much ready for final delivery. What about the bad ones with no engraving? They get dumped down the garbage chute right here. See you later. Now it's time to turn our tray of packages into a final product. Now these could go directly onto the motherboard of, say for example, a phone or a laptop. But in this case, it's going onto a high-performance SSD. Step one, we load in our blank PCBs. Then it goes through the PCB cleaner and into this bad boy, which lowers a metal screen over top of the PCB and then slides a squeegee across it, depositing just the right amount of solder paste onto all of the pads. Next, it goes into this machine for a machine vision inspection. You can actually see it spotted one little tiny error in the solder paste. So that's no big deal for this kind of thing. We can just pull it out and run it through again. Once our paste is perfect, our board goes into this line of pick and place machines, and they said I can press the start button. They're not the latest on the market, but they'll do about 2,000 components in 10 minutes, which is fine for the prototyping line that we're looking at today. You can actually see where the reels of tiny surface mount components are fed in and then placed rapid fire. Down at the end, we find the biggest components. So right here, we have our DRAM caches, and then in these two bays are trays of NAND flash. Now it's time for another inspection before our boards go into what I call the world's fanciest pizza oven. This Mama Jama has 10 heat zones, slowly ramping up and then towards the end, ramping down. This is because rapid changes in temperature can make BGA solder joints more brittle, and a brittle solder joint is a bad solder joint. Next comes the pizza cooler, then a third machine vision inspection. Finally, the finished boards come over to assembly, where you load your chassis onto the assembly jig and zippity zoppity fancy SSD. But there's one other environmental consideration for Kioxia, and it's a big one: earthquakes. With such high precision manufacturing, how do they deal with the roughly 1,500 earthquakes that hit Japan every year? To find out, we've ventured all the way down to the basement of one of the fabs to take an in-person look at the gigantic footings that suspend the entire building above the ground. They're made out of 4 different types of materials. This one's made of natural rubber, I think, and these softest ones go around the outside perimeter of the building. And then there are 3 other kinds that play different roles in maintaining the seismic stability of the entire fab. Because you never know what kind of earthquake you're gonna get. Some are more up and down, some are more side to side, and you gotta be ready for anything. The building we're under is supported by nearly 400 of these footings that allow it to move up to 60 centimeters, or about 2 feet, in any given direction. Now obviously they're gonna have to recalibrate their equipment to make sure everything's running correctly, but it's meant to dramatically reduce the impact. Maybe the coolest part though, is if you look carefully in the basement, you can see a little slit of daylight. And this is where it's coming from, where this entire building is completely decoupled from the foundation by those dampers. Here, check this out. You can't see it, but I moved it a little bit, like just a little. Massive thanks to Kioxia for having us out here. It really puts into perspective the hard work that goes into bringing these products to life. I don't think I'll ever take for granted the performance or storage density of NAND flash ever again. If you guys want to learn more, you can check them out at Kioxia.com. We'll have them linked down below. If you guys are looking for another video to watch, why not check out the time we collaborated with Kioxia to break a Guinness World Record, calculating more digits of pi than anybody ever has before.